Hello, Mr. Simpson here with our first video for Chapter 13, 13.1 Chemical Equilibria. As always, your learning objectives are listed here, so please pause the video and copy those into your notes. Now we're going to get into discussing equilibrium, and one of the biggest changes we have to make as we think about chemical reactions is the notion of the yields arrow. So as you can see in the first reaction, we see the traditional arrow that we've become accustomed to, and the idea of reactants yield products. In reality, the yield arrow is more like what you see here because reactions are reversible. Reactants can form products left to right as we have typically thought of reactions, but as my concentrations of products increase, those products can begin reacting, and the reaction can actually go in the reverse direction or right to left. This is the concept we're going to take a look at in this unit, and in this section, we're just going to have a brief introduction. Okay, so you can see the definition of equilibrium. We have not talked about rates yet. We will get to that in a later chapter, but rates is basically the speed of the reaction. When the rates of the forward and reverse reactions are equal and the concentrations of the reacting product species remain constant over time, we have reached equilibrium. You can see here we have two different graphs depicting this definition of equilibrium, and I want to be sure that we're careful here. In the first one, you see we have concentration versus time. In the second one, we have rate or speed versus time. Now, a common misconception is that people think that when you reach equilibrium that your concentrations are the same. Your concentrations are not necessarily equal. They just remain constant over time. So they stop changing. So you can see that is depicted here in this first graph, that as we would expect initially, we have, as I look back up at my reaction here at the top, N2O4 yields 2NO2. So initially we would expect to have only N2O4, our high amount of N2O4, and 0 NO2 as our reaction gets started. And because we have a greater concentration of N2O4, initially that reaction, those molecules are going to react faster, and we are going to get this curve that we see here and here. As the concentration of the NO2 will quickly increase, and then we reach this point in time in which equilibrium is achieved. Now notice the amount of concentrations for both are different, right? So the amount of NO2 I have and the amount of N2O4 I have are different amounts, but over time here, as we continue to move, those concentrations remain the same. As I think about the rate, and you don't need to worry about this equation yet. Here we haven't talked about the rate constant that you see here yet. But as we see here, again, the reaction is going to happen quickly. Initially for the reactants, because I have a lot of reactants that are colliding and reacting. And then we are going to have that same concept happen with our products as products start to form. And then we reach the point where the rate of the beginning of the forward equals the rate of the reverse. So meaning they are actually happening at the same speed. Okay, so don't make that same mistake when thinking about equilibrium. They are not the same. They just remain unchanged. Sorry, I mean, don't make that same mistake when thinking about concentration. Okay, so I just highlighted a couple of the points I just discussed here down at the bottom. If you want to pause the video and take a moment to jot those in your notes, please do so. Okay, that is all for our first video here on the idea, basically the overall idea of chemical equilibria. We will get into in the next video a little bit about the equilibrium constant and the quantitative relationships between the concentrations here during equilibrium.